Hi, my name is Reva Johnson. I'm a PhD student at Northwestern University doing my research at the RIC, and my advisors are Dr. John Sensinger, Dr. Levi Hargrove, and Dr. Todd Kuiken. And we've recently begun a collaboration with Dr. Conrad Cording, who's a computational neuroscientist at the RIC. And I want to tell you why we're excited about this collaboration and about what we've learned over the past year or so of this collaboration. So here at MEC, there's a lot of people doing great work on control systems for prostheses and on the mechanisms and prosthesis design and on implementing sensory feedback systems. And these are all really important and really worthy areas of research. But I'd also argue that we need to focus on what is the person doing when they're controlling this system? What is the user's behavior? What decisions is their brain having to make? I think that to design the best system, we need to understand how the person uses feedback during prosthesis movements. And the success or failure of this feedback depends on how the user integrates feedback with the movements that they're generating. And we don't really know yet how sensory feedback is used in prosthetics. We don't know if amputees continuously rely on feedback during movements, or if they use feedback mostly for correcting errors. And we really don't know if certain types of feedback are more useful than others. So these questions have all been answered for able-bodied subjects in the field of motor control with the help of a 17th century monk named Bayes. And Bayes started a field of probability and more recently has inspired almost an entire field of motor control. And I'm going to explain the central theory of his ideas by giving a simple example. So if Bayes was estimating how far he reached along a line, he's reaching his arm along that line, he has some knowledge of his arm's dynamics and of the dynamics of the world around him, and so he can predict when he moves his arm, where is it going to land. So he makes this prediction, and because neuron firing rates are noisy and because his brain has an imperfect understanding of these dynamics, that prediction has some uncertainty. And so that the width of that distribution represents how uncertain he is. The wider it is, the more uncertain he is about his prediction. Another way of thinking about this would be instead of just one dot of his prediction, it might be a scatter of dots. So the more scattered the dots, the wider that distribution would be. So then because our sensory system has some delays, about 100 or 150 milliseconds later, Bayes receives information from his sensory system about where his arm actually landed. So his senses tell him, whoops, your reach actually ended up here. And again, because his sensory system has an imperfect resolution, that sensory estimate has some uncertainty as well. So now he has these two streams of information, his prediction and his sensory information, and he needs to combine them to get the best possible estimate of where he landed. So he combines them by correcting his prediction with the sensory information, and he weights each of those according to the uncertainty. So if his prediction is very uncertain here, he will weight the sensory information more heavily. So you see that correction is shifted towards his sensory information because that's the more certain information. So this is the central theory of Bayesian models, is that your brain is estimating all sorts of variables. It's dealing with a lot of noisy information, and to get the best possible inference, the brain considers the uncertainty of each source of information and weights the optimal estimate accordingly. So these Bayesian models have been really useful for describing how our brains make decisions. They've been found to apply in a lot of different situations, and they've been really helpful in improving rehabilitation in many areas. They've been helpful in understanding the walking and reaching movements of stroke subjects and in improving the balance of children with cerebral palsy. And we think they could be ideal for understanding the high uncertainties of prosthesis control. So in prosthesis control, EMG is very noisy. We don't have accurate and precise control with prosthetics yet, and so presumably the feed-forward uncertainty is very high. And amputees rely predominantly on vision, and there isn't any clinically implemented sensory feedback systems yet, so feedback uncertainty is also high. So this balance between high feed-forward uncertainty and high feedback uncertainty makes these models really appropriate for describing how the brain makes decisions during prosthesis control. And there's also several implications if we think about sensory feedback in light of these Bayesian theories. For example, the impact of sensory feedback depends on the uncertainty of both the sensory and the motor information. So it really depends on how the person integrates their feed-forward and feedback information. So the goals of this project was to look at how prosthesis control conditions affect adaptation. So to get an understanding of how prosthesis control relates to this broader field of Bayesian motor control, we want to compare adaptation with 3 control interfaces. First is EMG, second is joint angle, and the third is joint torque. And this comparison enables a side-by-side comparison of prosthesis control and able-bodied control. And really the first question we need to ask is, do subjects develop an internal model with EMG? And is this internal model stronger or weaker than that we have with our able-bodied reaching? So to look at the strength of this internal model, we are going to borrow an experimental setup from the field of motor control, one that has been done in able-bodied subjects. And we're going to perturb a learned movement and measure adaptation. And what is found to be optimal in most situations is that feed-forward uncertainty generally increases adaptation. So that means that if you have, you're very uncertain about your control, as soon as you receive feedback that you made an error, you will correct quite a bit in response to that error on the next trial. Whereas feedback uncertainty generally decreases adaptation. So if you receive feedback but you're not sure of what exactly that feedback is telling you, you're less likely to use that feedback in adapting to the error on the next trial. So in this experiment, we tested trial-by-trial adaptation to visual perturbations. So what that means is on each trial, subjects were perturbed randomly in either a positive direction, negative direction, or no perturbation at all. And the task was to move this cursor around the circular single degree freedom track to try and hit this green box, the target. And subjects did this experiment 3 separate times in a randomized order, once using joint angle, once using joint torque, and one using EMG. And this upper right picture shows the joint angle setup, where a goniometer was measuring the angle of the elbow, and that angle is mapped directly to cursor angle as it traveled across the screen. And joint torque and joint EMG were both tested in an isometric setup, where the subject's elbow was restrained, and there's a torque sensor at the elbow that measures torque of elbow extension and maps that torque to cursor velocity. And then the EMG of the elbow extensors was also mapped to cursor velocity as it travels across the screen. So we also manipulated feedback uncertainty by presenting the cursor to the subject as either 1 dot, which is the low uncertainty condition, or as 5 dots, which is the high uncertainty condition. So in this condition, 5 dots were randomly displayed in a pattern to give the subject some uncertainty about where they landed. And here's an example of the experiment that each subject went through for each control interface. The first phase was to learn the dynamics, and so the subject sees the full path of the cursor across the screen and learns how to hit the target. And then visual feedback is extinguished until the end. And this is where it allows us to perturb the subject because they don't see the cursor in the middle of that reach. And then on some trials, instead of 1 dot, the subject is shown 5 dots. And again, this increases the uncertainty of the feedback that's displayed to the subject. So, our results, most importantly, subjects developed and adapted a simple internal model using EMG control. And we see that in this figure just by the fact that these adaptation rates are positive. We saw some adaptation to those perturbations. So what this figure tells us is adaptation rate on the y-axis and mean absolute error on the x-axis, which is the average error across the entire experiment with one control interface. And we see that as mean absolute error increases, adaptation rate increases. This makes sense if we think about mean error as some indication of feed-forward uncertainty. So if you're making a lot of errors, you're probably uncertain about your feed-forward control, and because you're uncertain when you receive feedback that you made an error, you rely on that feedback and adapt more in response to a perturbation. So this makes sense in Bayesian terms that as mean error increases, adaptation rate increases. And we also see a jump in adaptation rate from 5 dots to 1 dot. So these dashed lines here show us adaptation with high feedback uncertainty, the 5 dot condition, and then the solid lines show the 1 dot condition with low feedback uncertainty. And again, this makes sense in terms of the Bayesian model because adaptation rate increases as feedback uncertainty decreases. So the more certain you are of this feedback makes you more likely to correct on the next trial. So feedback uncertainty decrease adaptation. And one of the most exciting parts of our result is that adaptation was not significantly affected by control interface. So we don't see a big difference between angle, torque, and EMG, which are these orange, blue, and purple lines. And this is really exciting because this means that we don't need to form this separate understanding, separate model of EMG. All of the differences in adaptation are accounted for by how good or bad the subject was, how high their mean absolute error was in this experiment. And then to make sure that our able-bodied subjects were representative of amputee subjects, we tested 3 transradial amputees. Each transradial amputee did the experiment once using EMG control of the intact arm, which is shown here on the left. And then in the middle is each amputee doing the same experiment with their residual arm. And again, we see here that amputee subjects support Bayesian predictions. So you see the blue squares represent the low feedback uncertainty, and the green X's represent high feedback uncertainty. And as feedback uncertainty increases, adaptation decreased. So this supports Bayesian predictions. And what's interesting is that the amputee subjects adapted more with their intact arm. And from that, we can infer that since they were shown the same feedback across both conditions, that there was some difference in their feed-forward uncertainty. And if adaptation increases with feed-forward uncertainty, then we might be inferring that subjects were more certain when they're using EMG control of their residual arm. This might just be because they are more used to using that arm with EMG control. The part that doesn't make as much sense is that amputees with their intact arm adapted more than able-bodied subjects did with their intact arm. But this, we think, might just be due to our amputee subjects being older than our able-bodied subjects. But we have more results to analyze, and we'll look at if that trend holds with more subjects. So overall, our exciting result is that both amputee and able-bodied subjects formed an internal model using EMG control, and that subjects adapted in a way that supports Bayesian predictions of sensory motor adaptation. So this is encouraging that we can use these models to continue learning about and describing prosthesis control. And one implication of this result is that sensory feedback may be more helpful in building and adapting an internal model than in real-time feedback. But we'll have to do more studies to look more closely at this. And we can use Bayesian models as tools to understand the challenges that the brain is facing during prosthesis control, and we can also use that information to guide us in designing better prosthesis control systems. So with that, I'd like to thank CBM and my funding sources, and I'll take any questions.